Alright, today we're going to be going over chapter 4.6 in linear algebra, which is dimension. So dimension is the number of elements in a basis for a vector space. So for example, if we have the dimension of R2, we will have our two elements in the space because it is R2 of 1, 0 and 0, 1. A basis of a vector is a set of vectors that have two things. They'll have linear independence, which means that they don't depend on each other and they're not scalar multiples of each other, and also that it spans the vector space and it spans V. And finally, we'll have our theorem for dimension, which states that the number of elements in a given vector is a constant. So if you have your vector space of R3, your answer for the dimension is going to be 3. If you get a vector or something else as your dimension, then you know you messed up somewhere. Alright, so if we have our vector space of R squared, R cubed, and Rn, our dimension is just going to be whatever it is to the power 2. So for example, for R to the power R squared, is our dimension is going to be 2, meaning that we'll have two elements like we have here. We'll have two elements like we have here. But for Rn, we have n amount of elements. We'll have n amount of elements. And also, it doesn't matter how many things are in each element. That does not affect what we classify as an element. As you can see over here, we have A, B, and C, and nothing. But these all still count as an element, meaning that this has 3 elements, meaning that our dimension would be 3. Alright, now next up we have the dimensions of a matrix in P2 all the way up to P infinity. So when you're finding the dimension of a matrix, we're going to take our two values of our columns and rows and we're going to multiply them together, and that'll give us our dimension. So for example, if we have a matrix that's 2 by 2, our dimension will be 4. But if we have the dimensions of our matrix as m multiplied by n, then our dimension is going to be m multiplied by n. But for P2 all the way up to P infinity, it's a little different, because for P2, because we have our 1 x and then x squared, because of that 1, we're going to have it as n plus 1 as our dimension. So whatever number is the subscript, you just add 1 and that'll be your dimension. So for P2, the dimension will be 3. For Pn, our dimension will be n plus 1. But for P infinity, our dimension will still be infinity because it's infinite. Alright, so we have our 3 vectors of x1 plus x2 minus x3 is equal to 0. We have negative 2x1 minus x2 plus 2x3 is equal to 0. We have negative 1 plus 0x2 plus x3 gives us 0. So what we're going to do is we're going to put it into a matrix. So with this matrix, we'll have it as 1, 1, negative 1, because we just want our coefficients, and then we're going to have our row of zeros. So this will be negative 2, negative 1, and 2, and this will be negative 1, 0, and 1. So our first thing that we want to do with these kind of questions is we want to put this in the reduced row echelon form. So our first step is going to be, we're going to add R2. We're going to add to R1 to R2. And we're going to add R1 to R3. Which will give us 1, 1, negative 1 with all zeros. And 0, 1, 0, and 0, 1, 0. Now what we can do is we can subtract R2 from R3, which will clear that row, giving us 1, 1, negative 1, 0, 1, 0, 0, 0, 0, still equaling all zeros. And finally, our last step will be subtracting R2 from R1 to give us 1, 0, negative 1, 0, 1, 0, and 0, 0, 0, still equaling all zeros. Now, as we look here, what we can see is that our x3 is going to become a free variable because these two, I'll put in red, are our leading variables. Right there, those are our leading variables. Meaning that this -1 is going to be our free variable, which equates to our x3. So since our x3 is free, that means we can set it to anything. So what we're going to do is we're going to set our x3 is equal to t. Our x2 is going to be equal to 0 because we have a 0 here. Our x2 is going to be 0 because we have 1 and 0. That's just equals 0. And finally we're going to have x1 minus x3 gives us 0. So x1 minus x3 is equal to 0. Meaning that x1 is equal to x3, meaning x1 is equal to t. Now with this, what we're able to do is we're going to set them equal to each other in a matrix form. So we're going to have x1, x2, and x3 instead of equaling 0, 0, 0 like we had before. Since we found the reduced row echelon, we're able to set this to t, 0, and t. Now from here, what we can do is we can factor out a t to give us t multiplied by the matrix 0, 1, 0. Now, we're going to test for the basis for the solution space. So I'll put basis test. Because as you remember from the beginning, in order for the dimension to exist in the vector space, it has to be the basis of the vector space. So 1, 0, 1 is going to be linearly independent because there's nothing for it to be a scalar multiple with, and it's by itself, and it will span our vector space, meaning that it is a basis. So I'll write this down, linearly independent, and it spans the vector space. Now we're going to see that our t101 is going to be the only thing in our space, because t is just a constant, so we don't have to worry about that. And the only thing in our space is 101, meaning that since it's our only item in the space, our dimension is equal to 1.